Okay, so this paper that I'm going to be analyzing here is about pseudo-labeling and using pseudo-labels to train your model. So this paper was published by Dong-Hyun Lee, and it basically proposes a network that is being trained with both label data and unlabeled data simultaneously. So this is a new approach, and it can be very maybe deceiving at first, and he shows and proves the reason why this proposed idea could work. So he first shares that some of the way he's regularizing these methods is something equivalent to entropy regularization. So the way he's doing this, he's basically calculating the error. So he's proving that pseudo-labeling could work here. And he's saying, okay, it could work. I'm going to use these data sets that I know the values of the labels, and I'm going to train it with both unlabeled and labeled data, and I'm going to pretend that a subset is unlabeled, and I'm going to test the accuracy of these labels. So he's doing this way. He first starts saying that he wants to calculate the errors in here of the label and the loss rather of the label and unlabeled data. So he defines a function alpha. So after the model is being trained, he decides that the loss function, the total loss of the function, is going to be equal to the loss of the label function, which is this one right here, and then plus the error of the unlabeled inputs times an alpha function. So the alpha function here will be what he calls the value that is called to entropy regularization. So this will be our alpha function, and he defines a value alpha f, which apparently has been found as like a local value that has been found by other researchers, and he defines a time epoch time t times as per the epoch, and then at different time frames, 100 or 600, depending on how many epochs you're doing per run. So this changes depending on how many times you're training the model with what kind of data, label or unlabeled. And so then he uses entropy regularization. So this is a DNN network, the deep neural net network. And then he is saying this is how entropy regularization would work, which we already know. And then he explained why this loss function could work similarly to a function, logarithmic function. Is similar to a maximizer of a posterior distribution, the loss function, and he explains why in this function, which is the sum of the log of the posterior probability, meaning the probability that y of m is a label given that this input is given, right? And then this could represent the loss of the labeled data, and this effectively represents the loss of the unlabeled data. Now here he explains what n stands for. N is the number of labeled data, xm is the m label sample, alpha is a coefficient, in this case would be alpha, and then the log likelihood of a labeled data, which is the first term, and minimizing the entropy of the unlabeled data, which is the second term. So it's kind of drawing a parallel on this is why it works. It's similar to a posterior distribution function in here. So then he does training with pseudo-label as entropy regularization, meaning using alpha. He explained how he does this method. He said he predict the probability of 1 of k code via training with unlabeled and pseudo-labels simultaneously. So this is very important. This model is being trained with pseudo-labels and label data. The pseudo-labels are the ones obtained from the model. And then he says again that the method is equivalent to entropy regularization, which we already noticed. And he also plots the TSNE embedding as to see how the model makes clusters better when it's trained on pseudo-labels. And in this case, he's using the MNIST test data to see. And as we can see before, without unlabeled data, the model seems to be forming clusters, and after the pseudo-labels are added, it seems like the cluster are a little more differentiated from one another. And here he just goes and explains how his experiment is done and exactly how many labels he uses. He uses different training sets, so he does it several times with like subsets of labeled data to see the performance. So first he uses 100 labeled data, then 600, then 1,000, then 3,000, just to test how the performance will be. Okay, so here we're trying to do a code of basically what the paper was saying. First, we define the function of the deep neural network. We have a sequential model, and then we add an embedding layer, because in this case, we're going to be training text data simultaneously with pseudo-labels. We add a long short-term memory layer of 100 nodes, add a dropout layer of 0.5 probabilities, add a dense layer of 100 nodes, and finally output layer of 5 nodes at the end, and an activation function that uses softmax. Okay, so first this function will take the number of label samples, meaning how many label samples, similarly to what the paper said that it used. It first trained with a certain amount and then with another amount. So we do the same here. We also define the batch size, meaning how big of a portion the model is going to be trained on. We add the X and Y, which are supposedly the label values, and then X unlabel inputs, just to see how the model is going to do. And then it also the number of classes to the output has. Okay, so then we first make sure we split the data into tests and train, and then we make sure the data set is balanced, because many of the labels could be unbalanced, so make sure we're training with the similar amount. And then we split the data into train label, train Y train label, and also X unlabeled data. Then because we're going to be training in streaming, we create a GL function that will generate the train inputs for our model. And then we also do the same for the test generator. Here's the important part. We define our loss function. Okay, so our loss function is going to be multiply. The loss function for the label data is going to be just the regular value, just as stated in the paper. But the loss of the unlabeled data is going to be set as alpha, so it's going to be multiplied by alpha, and the unlabeled flag states basically the loss for that unlabeled data. So here alpha, we defined it earlier as well to be 0, just as in the paper. So for the first couple of epochs, until the first breaking point, or the first time is reached, the function will be 0 until T1, which is the first time, then it's going to be changed. And then, so that way our loss function could be adjusted by using alpha. So now here we're using Y minus the unlabeled flag value, meaning if we don't have any values here at the beginning, then the function will just be the loss. meaning the coefficients will just be equal to 1, and the entropy or the loss function is not going to be lost. Then we just define the accuracy, making sure we only take in the labels, label samples for that. And then here we just use a function to define what's going to happen at the end of the epoch. Basically, we need to adjust alpha at every epoch because our function alpha depends on the number of epochs. So we define epoch as if epoch is less than 10, in this case the numbers are lower because we are only running 100 epochs per iteration. So if we were to increase the values, I will adjust the values of alpha accordingly. So the first epoch is going, if it's less to 0, then the value of alpha should, if it's less than 10 epochs, then the value of alpha should be just 10. If the epochs are greater than or equal to 70, then the value of alpha should be 3. And if it's greater than 70, meaning almost reaching the max number of epochs, in this case for 100, then I should adjust the value of alpha. Then I keep track of the label prediction and also the unlabeled prediction just to see what values are added. So here something interesting is happening at the train generator. I'm actually concatenating the label and unlabel inputs, as well as the train label, the label, the white train that has labels, and also the pseudo labels made from the X inputs or the features that were on label. I'm adding that so that the model can continue to be trained on the pseudo labels that were created from the previous iteration.